another example for species competition. This is the situation in which we have changed a little bit of parameters. We have now x prime is equal to x times 1 minus x minus y, and y prime is equal to y times 1/2 minus 1/4 y minus 3/4 x. We compute the null lines. We have that x prime is equal to 0 for x equal to 0, or y equals minus x plus 1, and y prime is equal to 0 for y equal to 0, or y equals to minus 3x plus 2. So we can draw that. We have the vertical at the x equal to 0, that is x prime equal to 0, and then a horizontal line that is also x prime equal to 0. So these are the two null lines associated with x. And then we have the two null lines associated with y. We're only looking at the positive quadrant. And again, as before, the green lines, you move through them only in the vertical direction, and the red lines, you move through them only in the horizontal direction. Because we have the null lines that we have computed before, we can match the equilibria by picking one of each null lines. So we have x equal to 0, y equal to 0, x equal to 0, y equals minus 3x plus 2. We have y equals to minus x plus 1 matched with y equal to 0, and then matched with y equals to minus 3x plus 2. So we solved that and we found 4 equilibria: 0, 0, 0, 2, 1, 0, and 1/2. 1/2, 1/2. So as before, we compute the signs for x prime. That means we're dividing this positive quadrant by areas encircled by the green null lines. So we have the blue area and the green area. And we find that the blue area has x prime negative and the green area has x prime positive. We do the same for y prime. We divide our positive quadrant by areas that are bounded by our null lines associated to y. And then we find these two areas, the blue area and the green area. The blue area has y prime that is negative, and the green area has y prime that is positive. So we can divide our quadrant in these 4 areas in which we know the sign of x prime and y prime. Notice how it's pretty similar to what we did in the first case. The only thing that changes is the signs in the two rectangles, the little rectangles on the side that we have. We can draw some arrows. In the big positive area, everything is negative, so we're moving downwards and laterally, and the other side downwards and laterally, and the other two directions. And we can draw some extra lines, just to have some information. So now you have already this vague understanding that before we were moving everything towards 1/2, 1/2. Now it seems a lot of things are actually, like, things within the little two side triangles are actually seem to be moving away. Let's try to make this more precise. We can compute the Jacobian of df and dg. That becomes this matrix 1 minus 2x minus y minus x minus 3/4 y, and the last element is 1/2 minus 1/2 y minus 3/4 x. And we can compute the Jacobian at all our equilibria. For example, at 0, 0, we have the Jacobian being 1, 0, 0, 1/2. Or at 1, 0, we have minus 1, minus 1, 0, minus 1/4. In each case, we compute the eigenpairs. So we find that 0, 0 is associated with the eigenpairs 1, 1, 0, and 1/2, 0, 1. That gives us an unstable node. And 1, 0 is associated with the eigenpairs minus 1, 1, 0, minus 1/4, 4, minus 3. That gives us an asymptotically stable node. Both eigenvalues are negative. That means that in our plot, well, 0, 0 is unstable, so everything is moving away from it, while 1, 0 is stable, everything is moving towards it. We can do the same at 0, 2, and we find an asymptotically stable node, and at 1/2, 1/2, that gives us a stable node. So again, we find that 1/2, 1/2 has one direction in which things move towards it, and one direction in which things move away from it, and 0, 2 has everything moving towards it. Now that we have this representation, we can draw the connections. We don't really know if the line connecting 0, 0, well, there will be one line connecting 0, 0 and 1/2, 1/2. And we don't know, and then things will move away from it. So we try to connect these things in the most reasonable way, remembering that trajectories never cross. So we'll have some elements that come towards 1/2, 1/2 and then move away to the other two stable nodes. We'll have one connection between the origin and 1/2, 1/2, and everything away from it is moving to the two stable nodes. Notice how we can draw this in a more schematic way. And we can talk about basin of attractions. So 0, 2 is a stable node and has a basin of attraction that is roughly all this area that I drew in yellow. In the same way, 1, 0 has a basin of attraction that is like roughly the area I drew in green. And in the middle, we have a separatrix. That blue line indicates the distinction between everything that tends to 0, 2 and everything that tends to 1, 0. Depending on which side you are in this separatrix, you know what is going to happen. If you consider this in the condition of the two competing species, 1, 0 means that only the first species is left. 0, 2, it means that only the second species is left. So in this situation, what means is that either you start exactly at the separatrix, in which case the two species can end up coexisting as 1/2, 1/2. But if you start anywhere that is not exactly on the separatrix, given enough time, one of the two species is going to go extinct. So this is the final phase space that we can draw in this condition.